All right, for this last video of the unit, we're going to start off with just a recap of all the tests so far. I think that'll be helpful for us to see, just to make sure that we can put everything in context still, keep building that intuition up, and remind ourselves about what we have at our disposal. Then we're going to look at the ratio test. We'll do a small, not really proof of it, just a little outline of it, and then we'll talk about when we actually use it. And then I'll maybe look at an example or two. Then we have the root test, and we'll do the same thing. We won't really prove it fully. We'll just kind of give an outline of how that proof goes, and then we'll talk about when we use it and maybe do a couple of examples. Since the video is going to get kind of long, I don't want to go through the full proofs, but you can look those up online. There's probably tons of proofs all over the place. So let's go ahead and get this rolling. Here's a recap of our tests. We're going to start off with the divergence test. Remember, the divergence test says take a look at the limit of the terms themselves. If they don't go to zero, then the series has to converge, right? Diverge. Oh boy. Then we can also notice that the opposite is not true. If the terms go to zero, it's not true that the series is going to converge necessarily. We don't really know anything if the terms go to zero. We say the divergence test fails. The integral test says that as long as the function version of our series is positive, continuous, and decreasing, then the series and the integral are going to converge and diverge together. We know that if they both converge, they're not necessarily going to converge to the same thing. It's not likely that they do because of Riemann sums with integral approximations and stuff like that. Hopefully we have a good picture of that in our head now. The comparison test is really nice if we have a series that looks like it's similar to something like a p-series or a geometric series. We can do this nice comparison and show that if the series is greater than a divergent series, then the series diverges. And if our series is less than a convergent series, then the series converges. The limit comparison test can help us out a bit if it's hard to build that comparison. We just look at the ratio of the terms in the two series, and hopefully we get that equal to some non-zero number, because that means the two series converge and diverge together. If that limit is equal to 0 or infinity, then we eventually just get a comparison test, and you can try and string that together. For the alternating series test, if we have an alternating series, then as long as the size of the terms themselves is non-increasing and goes to 0, then the series converges, and we say at least conditionally, because remember there's this whole connection between conditional and absolute convergence that we have to investigate. So this is like the failed version of the divergence test. For an alternating series, it is enough that the terms go to 0 for us to say, yes, this thing converges. So that's something that's a little bit hard to keep track of. For a positive term series, if the terms go to 0, doesn't tell us a single thing. But if it was an alternating series, we know that it converges. Okay, let's talk about the ratio test. Here it is. The ratio test is going to look at a ratio of successive terms in a series. We're going to look at the next term divided by the current one, and we're going to try and look at the size of that ratio. If the ratio is small, that means the next term is really small in comparison to the current one, which is good if we're looking for convergence, because not only do we want the terms to go to 0, but you can think that we want them to go to 0 really quickly. We want them to get small fast enough that our series converges. So if the next term is a lot smaller than the current one over and over again, that might work. So here's what the ratio test says. We're looking again at positive terms, and we've got this ratio that we're looking at the limit as k goes to infinity of a sub k plus 1, the next term, over a sub k, the current term. And again, we said if that ratio is small, in between 0 and 1, then we're going to have this series converge. If the ratio is greater than 1, including going off to infinity, then the series diverges. And this annoying case of if the ratio is equal to 1, we don't know anything. The ratio test is inconclusive. Remember, again, positive terms on this, so we'll have to keep track of that. All right, we're going to split this proof into 3 cases, and I'm just going to talk through the outline of this. We are not going to get into the details. If you want to see more about this, there are tons of resources, I'm sure, or you can just message me and I can talk it through a little bit slower with a little bit more detail. But for now, let's just look at this case by case. Let's pretend that we found that this ratio was bigger than 1. Obviously, that means that the numerator is bigger than the denominator for all the k values, since it was true as k went out to infinity, or at least for all the meaningful k values, right? Because all the ones that matter are the terms really far into the series. Since the terms themselves are all positive, that means we have some positive sequence of terms that's increasing, right? Then, by the divergence test, we can clearly see that those terms are not going to go to 0. And so, the series diverges. Second case, this is the one that we want to see. We've got that ratio is some real number in between 0 and 1. Or essentially we're saying, let's pretend it's some small number. Then, for a large index n, we're going to look past that and we're going to say, okay, after that, really, really, really far into our series, this ratio a sub k plus 1 over a sub k is pretty close to r, right? If r is this ratio that's the limit, then we can approximate the limit by just saying when k is really big, it's approximately equal to r. That means for really big k values, you can multiply the denominator on both sides, and this is what we've got. So as k goes to infinity, we have this equality here, which is good. Okay, so for some large index n, and after that, we can say each of the next terms is really just this form, right? So we just multiply the current term by r, and then we do it again. We multiply that current term by r, and we multiply that current term by r again. So you'll notice we just keep getting bigger and bigger powers of r. As k goes to infinity, this tail of our series looks geometric. And that's why we can say if r is small, things are going to work well for us. So this is what we've got. This is supposed to be this partial sum s sub n. We take the first bunch of terms, add on this tail series, but we said that tail series is approximately geometric, right? And so the geometric series is going to converge under this condition. So essentially we'll say this ratio test shows that the tail of our series acts geometrically, and so we have this convergence criteria that's the same as the regular geometric series. If the limit itself is 1, we can do all the exact same stuff. But now, if r is 1, that means that each term is just the last term or the previous term near the tail, right? So we got this set up now. Instead of multiplying by r and then r squared and then r cubed, we're just multiplying by 1 and 1 and 1 and 1 each time. And so it just repeats the terms. Now, we do know that as k goes to infinity, a sub k goes to 0, because if it didn't, the divergence test would come into play. But the divergence test in this case is inconclusive. We don't know anything. All we know is that the terms eventually do go to 0. So that's why the ratio test is inconclusive in this case. Okay, so let's repeat this. We're looking at successive terms, looking for a small ratio. We're looking for positive terms only, which means that if we do have alternating stuff, we're going to have to figure that part out. When do we use the ratio test? When is it helpful? Why is it a good test to apply sometimes? Well, we've got this division of a sub k plus 1 over a sub k, and so we're going to try and take advantage of that. We're going to try and find series where when you do this division, things happen. Exponentials and factorials, specifically, have really nice ways of canceling stuff. Hopefully, it's easy enough to see why this is equal to a. You can subtract exponents, right? Or you could say this is a multiplied by itself, k plus 1 times. And on the bottom is a multiplied by itself, k times. And so, really, you've got, let me write it this way. I'll say, really, you could say that this is a to the 1 times a to the k over a to the k, right? Add the exponents together. But then if these things cancel out, you're just left with a. So exponentials work out really nicely. Factorials work out really nicely too, because for a factorial, k plus 1 factorial over k factorial, we've seen this a little bit before. But let me write this out. This is k plus 1 times k minus 1 times over and over and over again until we get to like 3 times 2 times 1. And in the denominator, k factorial is just k times k minus 1 times all those values down to 3 times 2 times 1. And so hopefully we can see that all these things cancel out in the numerator and denominator, and we're just left with this k plus 1 here. So factorials are really nice, specifically because they're hard to deal with in other cases. They're not nice to work with the integral test because we don't know how to integrate something with a factorial. It's not a continuous function. Comparison tests can be sometimes difficult with factorials. Maybe you've already seen that. You can apply some comparison tests to things with factorials, but sometimes it's really hard. So the ratio test is going to be really nice for factorials specifically, but also things like exponentials will work out nicely too. So here in this first example, you might notice that this is not a positive term series. So you could apply the alternating series test, and you can hopefully see that this is going to converge at least conditionally, right? Because the k factorial has a higher growth rate than an exponential, and so this limit of terms is going to go to 0. But let's take a look at the absolute value and see if it converges absolutely. So we're going to look at this sum from k equals 1 up to infinity of 5 to the k over k factorial. And we're going to set up our ratio test. And as a reminder, the r, this ratio, is going to be the limit as k goes to infinity of the k plus first term over the kth term. I want to show you what I mean by that. Here, r is equal to the limit as k goes to infinity of this with a k plus 1 in it instead of k. So what I'm going to do is I'm going to put k plus 1 right in here and right in here. So I've got 5 to the k plus 1 over k plus 1 factorial. And I'm going to divide that by the a sub kth term, and this is 5 to the k over k factorial. Division like this looks really nasty, so I'm going to write this as a limit as k goes to infinity of 5 to the k plus 1 over k plus 1 factorial times k factorial over 5 to the k. And now we can start taking advantage of those cancellation properties, right? 5 to the k plus 1 over 5 to the k, that's really just 5 in the numerator. And a k factorial over k plus 1 factorial is really just a k plus 1 in the denominator with those cancellation things. Go back a slide if you want to see it, but that's how these things are going to cancel nicely. Now, this limit is an easy one to find. When k goes to infinity, the limit is 0. Since this limit is 0, we can say this series converges absolutely. Because remember, we looked at only the positive term versions. We took an absolute value of all this stuff. Neat. For this second one, we can set that one up as well, and we can say r is going to be equal to the limit as k goes to infinity. I'm going to put a big fraction bar here, and I've got a k plus 1 squared minus 1 over 2e to the k plus 1 over k squared minus 1 over 2e to the k. That's my k plus first term in the top, my kth term in the bottom. Eventually, you should probably, I think, just start writing it like this. K plus 1 squared minus 1 over 2e to the k plus 1 times 2e to the k over k squared minus 1. Notice the exponentials are going to cancel out. And so this limit is really going to have a 2e on the bottom. Whoops, I need that to be a straighter line. There we go. And then it's going to still have this k squared minus 1. And on the top, we've got a k plus 1 squared minus 1. You can do some L'Hopital's rule on this if you'd like. I'll let you fill in the blanks. And you'll find that this is going to be 1 over 2e. That's a small number, smaller than 1, meaning this series converges. So that's how you can apply the ratio test. All right, let's take a look at the root test here. Instead of looking at a ratio of terms now, the main thing is we're going to be looking at the kth root of the kth term. So instead of dividing the next term by the current one, we're going to look at the root of the term, but we're going to look at the kth root specifically. Now, this is going to get a little bit tricky if we think about this limit. So we've got rho, instead of r now, rho is equal to the root, the kth root of a sub k. Again, non-negative terms. So if we do have some alternating series, we're going to have to look at absolute values to apply this. And we have the same conditions applying here. So notice exact same results of the ratio test, but we're getting this limit a little bit differently. Instead of dividing, we're looking at a kth root. So this is going to be similar. The proof is similar. We're going to make the tail of this series look geometric again. I'm not going to spend too much time on this proof outline, but hopefully we can see a little bit about what's going on right here. Each term is eventually going to look like this rho limit raised to the k. that's going to look geometric. As long as rho is our ratio for our geometric series, all the same conclusions are going to apply. So connect this to the ratio test. Again, if you want to see more details, there are plenty of proofs out there for this, and you can definitely ask me if you'd like. Okay, when do we use the root test? When is it going to be helpful? These roots can be really annoying to deal with. So what we're going to try and do is take a look at taking advantage of the kth root. So exponentials with k in the exponent are really good candidates because the kth root is going to cancel out that exponential. So if we had a regular exponential, it might be a geometric series. So we're going to look for something a little bit more complicated. Most of the time, it's going to be these sometimes we'll call them hyperexponentials, where you have k in the base and k in the exponent, right? So it's not really a geometric series because it's not a fixed ratio, right? This k plus 4 is changing as k changes. So that'll be really nicely. Also, things with fractions aren't too bad because roots can split up on fractions and products pretty nicely. But most of the time, you're going to be looking for this k up in an exponent. So this first example is in my mind, classic root test stuff. I'm not going to worry about the fact that when I evaluate this at 1, as k equals 1, that I do get a negative term a little bit. It's no big deal. So I'm not going to worry too much about that because eventually they're going to turn out to be non-negative, right? So what I'm going to do is remind myself that rho is equal to the limit as k goes to infinity of the kth root of a sub k. So for this one, I'm going to say rho is equal to the limit as k goes to infinity of the kth root of 2k cubed minus 5k plus 1 over 3k cubed plus 4k squared minus 1, all raised to the k. Now, the beauty of the root test here is that the kth root and this big exponent of k cancel each other out. So here's our big kth root, our exponent of k. So really, this is a limit as k goes to infinity of just the 2k cubed minus 5k plus 1 over 3k cubed plus 4k squared minus 1. And hey, notice you can either do L'Hopital's rule on this or you can just look at these first terms. And either way, this limit is going to be 2/3. Specifically, I'll say rho is smaller than 1. It's small, and that means this series converges. We can do the same thing with this one. I'm going to throw some absolute values on here right away because I've got this -2, right? So maybe what you can do is write it this way. You could say this is a series from k equals 1 up to infinity of -1 to the k, 2 to the k, over 3 times k to the k. And then once you throw the absolute values on it, you can see pretty clearly that that -1 to the k is going to just turn into 1. So when we look at the absolute values here, I'll say rho is equal to the limit as k goes to infinity of the kth root of 2 to the k over 3 times k to the k. And this is really the limit as k goes to infinity of the kth root of 2 to the k over the kth root of 3 times the kth root of k to the k. These two things are going to have some nice cancellation. So you're going to have a limit as k goes to infinity of 2 over the kth root of 3 times k. This kth root of 3, you can show that this is going to end up going to 1 because you could write it as 3 to the 1 over k, and then that exponent goes to 0. And so this whole thing is going to go to 0 because you're going to divide by 1 times infinity. That's small. We're okay. All we needed was that rho has to be in between these two things. So that means that this series converges. And then what we can say is that it converges absolutely. Because remember, this was an alternating series that we looked at the absolute value of. Since the absolute value of it converged, our series converges absolutely. So Ratio and root test, that's what we've got. For the ratio test, factorials are going to be the real big winner here for the ratio test because of those nice cancellations. And for the root test, look for those big exponents of k where it's not actually geometric, but we still have a lot of exponentials. Once you've got those things figured out, everything should go nicely. Keep in mind that the ratio and root test only work for positive term series. So what you need to do is throw absolute values on everything and see what happens here. Hopefully that's a helpful thing to see, and we will work more with these in our next unit. But for now, make sure you've got all these series tests figured out and kind of in your back pocket ready to go. Good luck as you get ready for the next exam, and if you have any questions, let me know.